Good day, I'm Sharon. Our group topic is the mathematical model of RQ inventory policy under limited storage space for continuous and periodic review policies with backlog and loss sales. In an RQ policy, an order amount of Q is placed when the inventory level falls to reorder point R. Let us look at the comparisons of continuous review system and periodic review system. For continuous review system, the inventory levels are monitored constantly, have fixed order size but varying order intervals. Now, replenishment order is placed when on-hand inventory falls on or below reorder point. Then for periodic review system, the inventory levels are reviewed on a periodic schedule. It can be weekly or monthly. Then variable order size but fixed order interval. Then the replenishment usually occurs between review periods. So there is an average delay of half a period before the order is placed. Mostly the RQ policy is for a continuous review model, whereas an order up the level policy is for periodic review. But some industrial users still prefer RQ policy and use it with the periodic review system. And a case study is on a fast-moving item inventory at a distribution center of a healthcare company in Thailand. The objective is to determine the optimal or near optimal R and Q, which minimize the total inventory management cost that consists of fixed ordering costs, inventory holding costs for internal storage space, shortage costs, and over-ordering costs. Then before looking at the result, I pass the floor to Mingjun and Kwanlang to present the methodology part.
Hi, my name is Mingjun. I'm presenting about the methodology. So the first method is probability distribution of demand during varying lead time. So the stock case day and discrete behavior of the demand data and lead time are modeled using the distribution of demand during varying lead time. Note that with the historical demand data and lead time, we can list all possible value of random demand with xd equal to small xd, random lead time xl equal to small xl, and empirically derive their probability mass function with fxd and fxl. So demand during a given lead time xl, as we can see this function, at the end we can summarize it, is the summation of I equal to 1 to xl with the function of xdi, where xdi is independently and identically distributed random variable with fxd, then its probability is, we can see this function, finally we can summarize it, is the product of fxdi from I equals to 1 to l. Combining with fxl gives the probability of demand during varying lead time. So we can see this function is equal to the summation of L from L with the function of P x equal to x, given that xl equal to small xl, we times P xl equal to small xl. So next, the second method is probability of stock out and probability of over ordering. So we can see the figure 1 inventory level in a replenishment cycle. So given that the value of Q, R, and W in a replenishment cycle IP, OH, shortage amount, and overorder amount, while the probability of stock out, as we can see the figure 1. From this line is without undershoot, and this line is with undershoot. So next, figure 2, the probability of stock out and over-ordering under distribution of demand during lead time. As we can see, this figure suppose that fx is a normal. The probability of stock out may occur the right tail of fx and toward the end of an order cycle, whereas the probability of over-ordering may occur at the left tail of fx, so at the beginning of the next order cycle, and depends on the value of x in the previous cycle. Next, The third method is inventory review and demand during stock up. So there is a difference between continuous and periodic review. Periodic review is in a continuous review, a replenishment order is placed when OH fall on or below R. As mentioned earlier, for periodic review, there is an average delay of half a period before the order is placed. So an undershoot amount of average demand divided by 2 units is the difference between R and OH at the point of ordering. So it will affect PS and ES, as we can see this formula. So we consider lost sales and backlog cases. So the difference between of both is the amount of OH that is replenished at the beginning of a cycle, which would be Q for lost sales and Q minus ES for the backlog. So next, the fourth method is expected over ordered amount. So to derive EO, we have to consider the expected OH at the end of cycle EOHN. So for the continuous review, we can see this function EOHN. We summarize it all. At the end, we get R minus the mean plus ESC. So for periodic review, we can adjust with the undershoot amount with EOHN is equal to R minus average demand minus 2 divided by 2 minus the mean plus ESP. So from this table, on-hand inventory in a cycle for 4 cases of RQ inventory policy. So we can express of the random OH. So as we can see, we derive by replacing the mean with X. Then OH can be derived from the difference between random OH at the beginning of the cycle OH begin and W. So these are the 4 cases of policy in the 5, and the expected inventory position at the time of ordering IP is used to generalize the formula for the 4 cases. So it's similar to PO, is generalized according to the 6 is this one. So as just now I mentioned, using the corresponding IP for 5 and 6 with these types of formula. So we can see that both EO and PO are function of Q and R. So that's all from me. Thank you.
Hi, I am Guan Liang, and so I will continue with the methodology part for the part 5. And so the part 5 of the methodology is to find the average inventory management cost per cycle, which is generally known as the total cost. Okay, so in this case study, there are 4 main components of the inventory management costs, which is the ordering cost, the shortage cost, the holding cost, and last but not least, the over ordering cost. So the ordering cost is basically is represented by the symbol CP, and then the shortage cost is CS multiplied with the ES, which is the expected amount of shortage, and then the expected over ordering cost is the formula of the ordering cost multiplied by the square of EO, which is the expected over order amount, divided by 2 times the mean D, which is the average demand. And lastly, for the holding cost, is actually charged based on the average OH, which is the on-hand inventory. Basically, there are 3 types of on-hand inventory, which is at the beginning of the cycle, end of the cycle or at the time of ordering. So the length of the cycle is calculated by the formula Q, the order amount divided by the average demand. So here comes the average total cost per period. So we just total up everything, all the formulas, and divide by Q plus the expected amount of shortage to get the average total cost per period. So next, after we have obtained the average inventory management cost, then we'll continue to the part 6 of the methodology, which is to formulate the mathematical model to find R and Q. So what is this method doing is generally they are taking the first derivative of the total cost with respect to both R and Q, and then setting both equations to 0 and then solving them. So this is the general form of with respect to Q and R. So basically the formula is just taking the first derivative of the total cost and then equals to 0. And then after that, after we have obtained the formula, so the next thing is we solve the equations result in the general expression for Q and then for R. So we just rearrange it so to make Q and R as our subject. So this is the formula we get for Q and R. Then we can proceed to our next methodology to do the iteration for Q and R. How does the step is going to work? So there are 4 steps to determine the model for R and Q. So the first step is the initialization step. So at the initialization step, since the stopping rule is based on the total cost, we have to first initialize the total cost equals to M, which is a large number, and then eventually the total cost will become lower and better. And second, we need to from the amount of demand and amount of loss, we need to compute the average demand and the average loss. And then also we need to fit a function of the amount of demand and the function for the amount of loss. And next, we need to compute all x for each amount of loss and the probability such that x equals to this formula. And the next thing is we need to compute the average demand based on the average lead time by using the formula average demand times the average lead time. And then we need to know the maximum amount of x, and then also the function x. And then lastly, we need to compute the initial Q by using this formula square root of 2 times average demand times 50 purchasing cost divided by the holding cost. Okay, so after the initialization step, in step 2 we need to compute the new R value. So in our case study, generally there are 4 different cases, and for the 4 different cases actually we need to compute 4 main value for us to calculate the new R value. So the 4 main value are the PS, which is the probability of shortage, the ES, the expected number of shortage, the EO, expected over order amount, and also the probability of over order amount. So after we get the 4 value for each cases, we can compute the new R value. And then after we get this R new, we need to compute the modulus value of R minus R new in order to find the minimum value for R minus R new for the 4 cases. So for us to get the minimum value, the R new actually has to be the largest among the 4 cases. We need to know which one is has the largest R new, and so we can get the minimum R minus R new value. So we will choose the R new with the most minimum R minus R new value as our new R new, sorry. Okay, so in step 3, after we have known our new which one is our new R, we will compute our new Q. So we compute at first we need to compute the expected shortage amount, DES, with R that we have obtained from step 2. And then the next step is basically the same as to compute the new R, as there are 4 different cases. That's why we need to compute the probability of amount, the expected order amount, and also we need to compute the Q by using the formula that we have derived previously. And then the next thing is the same as well as the R. We need to find out the minimum Q minus Q new, and then we need to update our Q with the new Q that we have obtained, just the same as the previous R. And then lastly, we need to update our total cost by the value of Q and R that we have calculated just now. And then the step 4 is actually we need to repeat steps 2 and 3 if the total cost improves from the previous value. Otherwise, if the total cost remain constant, then we can stop the iteration and the value of Q and R is the optimal value of our model. And that's all for the methodology part.
Now let me continue to the results of the study. This is the real data used to determine the optimal or near optimal RQ solutions. We have 4 cases which are continuous with backlog, periodic with backlog, continuous with lost cells, and periodic with lost cells. From the results, we notice that the only difference between continuous review solution and periodic review solutions is in R but not in Q. And this is not coincidental because the difference is equal to the expected understood amount. Figure 4 shows the optimal solution and the cost components for each case. Let's compare the continuous and periodic model. Both have the same Q. Periodic review has a higher R in order to compensate for the understood but expected number of shortage, and shortage costs remain slightly higher. Holding costs and over-ordering costs are higher for a continuous review model. Then periodic review has a slightly higher total cost and longer cycle time, which lead to the same average total cost per day. Then both have no difference in terms of inventory management, cost, and performance. Then for backlog and lost cells, R is higher for lost cells and Q is higher for backlog because it must satisfy demands during stockout. Higher R leads to higher expected number of over-ordering and probability of over-ordering for lost cells. Higher Q leads to higher holding costs for backlog. Backlog has a higher total cost, but it has a longer cycle length, which leads to the average total cost per period reduced. For the same cost component, backlog is more cost-effective than lost cells. In conclusion, periodic review problem can be solved by simply solving the continuous review problem and adding the understood amount to the optimum R, while the optimum Q remains the same for both review policies, and both review systems perform nearly the same given that the understood amount is explicitly considered. For future work, further investigation for periodic review cases can be done, and we can extend the model to multiple products sharing the same storage space. That's all from us. Thank you.